One of my Patreons, shout out to Ravi, wanted to know why when they pour a glass of spirit, does it smell less alcoholic when they let it sit for like 10 minutes? More specifically, they wanted to know the science behind this, and this isn't the first time that I've been asked this question. So if you have also... Sal just took my microphone. So if you've also noticed this, experienced this, let me know in the comments. And the quick answer to this is essentially that you're like getting desensitized to ethanol. The more you drink, or even within a sitting, right? You're not really smelling the ethanol anymore. You're getting used to it. But that's not the answer that I'm going for today, because that only explains the physiological part of what's happening, which is definitely a thing. But there's also a chemistry-based explanation for what's happening in your glass that impacts the way we're perceiving spirits, impacts the way that spirits smell. And that's what I think we should discuss today. That's what we are going to discuss today. So today we're going to talk about the molecular dynamics of a spirit in a glass and the fluid dynamics that govern its journey through the headspace of a glass. And yeah, we're going to do some math in this video, so get ready. Yeah, I know you guys are real booze nerds if you heard me say molecular dynamics and fluid dynamics and you didn't immediately turn off this video. So welcome back, everyone. I'm Robin from This Blog's Neat, and before we dive into molecular dynamics, I just want to briefly talk about the chemical composition of spirits. Because when you nose and taste things, what we're doing is we are detecting the various chemical compounds that are within that thing. So in spirits, we're picking up these various chemicals using our chemical sensors that are built into our nasal cavity and our tongue and mouth. So spirits, whether they are aged, unaged, rum, whiskey, brandy, mezcal, all of that, they're mostly made up of ethanol and water. I mean, like 99 weight percent. That other 1% we refer to as congeners. You've probably heard this word before. And that means what makes whiskey, rum, brandy different from one another is within that 1% composition right there. And as someone who has studied the congeners in spirits, right, looked at the chemical composition of spirits, I can tell you that there's a lot of overlap between those molecules. There's a lot of similarities there. So today I'm not going to focus on one type of spirit in particular. However, I've got a few references here that are studying whiskeys or their focus is on whiskeys. But the trends that I'm going to discuss today will be applicable to all spirits. So within that small fraction of congeners, we have hundreds to thousands, if that spirit is aged, of different chemical compounds. And not all of them are going to be flavor active, meaning they're not all going to elicit a response in our nose or in our mouth that we go like, oh, that smells like strawberries, tastes like banana. But in some way or another, they will impact how we perceive spirits. But the most flavor active compounds in spirits are esters. You've heard me talk about esters a ton. Aldehydes, carboxylic acids, higher alcohols, meaning other alcohols that are not ethanol. Phenols, sulfur compounds. I'm sure I'm missing something, but this is typically the most flavor active types of compounds that we'll come across. Some flavor and aroma compounds will overpower others. Some will complement others, but all in all, we're perceiving them all together as a symphony rather than as individual notes. I just kind of want to point that out there. Smelling and tasting is really a beautiful interplay between all of the volatile aroma compounds. So as we know, as we just stated, right, all of these flavor and aroma compounds, all of these congeners are existing in a solvent that is a mixture of ethanol and water. And the congeners all have varying degrees of hydrophobicity. And because ethanol and water have, we'll call it an interesting relationship. We're not going to dive into super deep into their relationship today. These compounds, these congeners, aren't perfectly dispersed throughout the entire solution, right? Throughout the entire spirit. That's because some of them stick more closely to ethanol, especially the more hydrophobic ones. And ethanol, interestingly enough, tends to gravitate towards the very, 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 very top, right? This gas liquid interface, the very top of the surface. So that means if we zoom into the surface of your spirit, there's going to be a lot of ethanol molecules right on the top. And that's relative to the amount that's just underneath that. We're still at the surface here, keep in mind. So both of these papers here, holding a microphone and papers at the same time is challenging. But both of these papers here showed this, right? We have Dilution of Whiskey, the Molecular Perspective, published in 2017 by Carlson and Friedman. And then we have Molecular Dynamic Simulations of Flavor Molecules in Scotch Whiskey by Shuttleworth et al., published in the Journal of Molecular Liquids in 2023, so last year. I should say who the rest of the et al. Is. I've been et al. And Shuttleworth, Apostolo, Camp, Connor, Harrison, Jack, Clark, Nicholas. So in both of these studies, in both of these papers, they use simulations to study essentially the dispersion of specific flavor molecules in ethanol and water mixtures at varying ABVs, meaning where are these molecules found? Are they found at the liquid vapor interface or the gas liquid interface, or are they located in the bulk solution? And how does that change with varying ABVs? They both started with looking at pure ethanol and water mixtures. And as I mentioned, ethanol has a clear preference for the interface. However, as the concentration of ethanol increases, meaning as ABV increases, it moves into the bulk. And one paper indicated that it does start to form little clusters. This aggregation is a random process, and at concentrations between like 59% to 77% ABV, this is like where we see some cask strength spirits, that gives rise to the greatest deviation from ideal mixing behavior. So now if we start to add various molecules with varying hydrophobicities, we can see where those tend to gravitate, where they prefer to orient themselves. Both of these papers looked at various compounds. So we'll talk about octane, octanol, octanol, octanoic acid, ethyl hexanoate, and guaiacol. And I'll try to breeze over them pretty quickly. These are all different types of congeners that you'll come across. Not all of them that you'll come across. I'll talk about that in a second. Keep in mind, these papers looked at one analyte at a time rather than a mixture of all of them in the ethanol and water. So we'll start with octane, which is an alkane that is highly hydrophobic. And you're not going to find octane in spirits. It's not flavor active. It's not, to my knowledge, is not found in spirits unless there's some weird contamination. But they chose octane to start with because it is so hydrophobic, and they wanted it to represent hydrophobic compounds, and it has a similar molecular structure and mass as the other compounds that they studied. Now, because it is so highly hydrophobic, octane was concentrated at the gas-liquid interface for all ABVs that they looked at. So it never really went into the bulk, even at 100% ethanol, which I find interesting. So super hydrophobic, it's going to stay at that gas-liquid interface, right at the surface. So next they looked at octanol, which is an alcohol with a waxy aroma that we do actually come across in spirits. And the simulation showed that at ethanol concentrations below 41% ABV, it tended to gravitate towards the gas-liquid interface. But as the ABV increased, it started to move a little bit towards the bulk, but still had preference at the gas-liquid interface. Next, they looked at octanol. Tell me how you would pronounce it. If you're a chemist, I'm totally forgetting how to pronounce this. But this is an aldehyde with a soapy, oily aroma. It behaves the same as octanol. And I don't know that you'll find this in spirits. However, acetaldehyde is the most common aldehyde that's found in spirits. It's much smaller. It has a much shorter chain than octanol, which would make it more miscible in water. So based on this, I would guess that acetaldehyde will probably still reside at the gas-liquid interface, but also have some dispersion in the bulk because it's more miscible in water. Octanoic acid, this is a carboxylic acid that smells goaty, like goat cheese, and at ABVs at 29% and below, so super diluted spirits, it is concentrated at the gas-liquid interface. However, at 41% and above, it starts to gravitate towards the bulk. Again, it's still located primarily at the gas-liquid interface, but there's a lot more in the bulk than the other compounds that I've listed. Now, octanoic acid is found in spirits. However, it's not the most common carboxylic acid that you'll find in spirits. That's acetic acid. And acetic acid, similar to acetaldehyde, is a shorter chain. So it'll be more miscible in water, and you'll probably see more of it dissolved in the bulk solution versus right at the surface. Ethyl hexanoate is an ester, and this smells appley, fruity, and it behaves the same as octanoic acid. And ethyl hexanoate is one of the more common esters found in spirits. However, ethyl acetate surpasses it by far as the most abundant ester in spirits. So ethyl acetate, again, being smaller, will be more miscible in water, so it should be more concentrated in the bulk. Again, we'll probably prefer the gas-liquid interface. Yeah, I think you're seeing the trends here. Last but not least, guaiacol is a phenol that's smoky. Most are. And it's one of the more abundant phenols in spirits, especially peated scotches. And at 45% ABV and below, it's located at the surface. However, as the ABV increases, it starts to gravitate towards the bulk, and that's because ethanol moves into the bulk and forms those clusters and brings guaiacol with it, right? So that kind of explains what's happening with all of the various congeners that I've listed. So in summary, ethanol prefers the gas-liquid interface, especially at lower ABVs. All of the compounds, aside from octane, are miscible in both ethanol and water, but do prefer to be with ethanol at the gas-liquid interface. The longer the carbon chain, the less miscible in water, and the more likely the compound will prefer the gas-liquid interface versus the bulk. So we'd be more likely to observe some of the more abundant compounds that I listed, right, like acetic acid, ethyl acetate, in the bulk rather than these larger congeners that are more concentrated at the gas-liquid interface. Now, there are a couple things that I want to point out. First, keep in mind these papers only studied 5 congeners, right? And as I said, there's like hundreds to thousands. But I think they do show a pretty good representation of where these congeners might be located, at least at the surface of our spirit. Now, does this mean that we should be diluting all of our spirits to bring all those congeners to the surface? No, not necessarily. Concentration does matter, and this video isn't about spirit dilution, but I will say diluting your spirits also dilutes the flavor compounds. Anyway, the next point I wanted to make is that the distance of space that was used in the simulations was on the order of angstroms. So the distance between the surface and the bulk was 20 angstroms. And angstroms are really, really just unfathomably small. You can fit 10 million angstroms in 1 millimeter. So looking at these results, right, we're essentially zooming into the very top layer of the molecules in our glass of spirit, right, to see how those molecules are behaving. This is not representative of what's in the entire glass. We're not seeing a gradient within the glass on the macro scale, right? A concentration gradient. That's not the case. This is right at the surface. But obviously, I thought these results were important enough to impact the way we perceive spirits, which is why I brought them up. So, what does all that have to do with how we smell and taste spirits, and how that changes as the spirit sits in the glass? In order for us to detect these chemical compounds, we need them to reach our olfactory cells. That means we need them to make it to the gas-liquid interface in our glass and then evaporate into the headspace of the glass. So when we sniff, I don't like how glasses smell when they just come out of the dishwasher, but when we sniff, they go into our nasal cavity and to the olfactory epithelium, where they combine with those receptors. So we pour our spirit into a glass. All those molecules are randomly mixed, but let's assume that the molecules right at the surface take an insignificant amount of time to orient themselves, right? To orient themselves where they want to be. Ethanol and the other congeners are most likely going to be right at the surface. So we have ethanol molecules concentrated at the surface and the more hydrophobic compounds at the surface. But now we need those molecules to vaporize. And each molecule, as you might guess, has varying degrees of volatility, meaning some molecules will move into the gas phase more readily than others. We refer to this as their vapor pressure, and this is going to depend on the concentration of those molecules in the spirit, as well as the ambient temperature and pressure. But overall, the larger the molecule is, the less volatile it is, which means the lower the vapor pressure. So smaller molecules will have higher volatility and therefore higher vapor pressure. So as you might guess, ethanol has a higher vapor pressure than water. This makes sense, right? Because ethanol boils at a lower temperature than water. So for a mixture of ethanol and water, the vapor pressures of each substance is actually going to be less than that of the pure substance, and it's going to be proportional to how much is in that mixture. And this goes for any of the volatile compounds in the spirit. The vapor pressure of that compound will be proportional to how much is in the liquid, which will be much less than the vapor pressure of the pure liquid. And this makes sense, right? The more that there is of something in our spirit, the more we'll be able to smell it. So as I've mentioned, a spirit is mostly ethanol and water, which means that the vapor in the headspace of your glass, right, above the liquid, will be made up of mostly ethanol, with a little bit of water. But these aren't the compounds that we're interested in smelling, right? We want the esters and the aldehydes and the phenols and the carboxylic acids and the higher alcohols. And trust me, we want the larger compounds of these, the bigger molecules that are still volatile, right? Rather than the more abundant, like ethyl acetate, acetic acid, acetaldehyde. So those longer carbon chain molecules, those bigger molecules, will have lower concentrations and lower vapor pressures than the shorter chain molecules. However, we do know that they prefer the gas-liquid interface, which is good news. So what do they need to get into from the liquid right at the surface into the gas phase, into the headspace of the glass, so that we're able to detect them? They need time. Now, how much time do they need? This is where we get to do the math part. So let's figure out how long it takes for, say, ethyl hexanoate to reach a concentration within the detection threshold of us, of humans, at the very top of the Glencairn. And let's see how that compares to how long it takes ethanol to do the same. We're going to calculate this, but please note that these calculations are estimates that are not taking into account a lot of things like liquid or air movement in the glass or near the glass. They're not taking into account that you're like pouring the spirit into the glass. We're doing this calculation as if we have a Glencairn in a completely stagnant room, and at time equals 0, right? We start our stopwatch and 1.5 ounces of spirit just magically appears into the glass. We're also going to assume ideal mixing conditions, which, as I previously stated, is not the most accurate representation of real life in our glass. Nevertheless, that's what we're moving forward with. We're also going to use a number of equations that most of which I have not even looked at since grad school, so bear with me here. And I'm going to include the calculations for anyone who is super nerdy enough. I'm sure this is a future Robin problem who's editing the video. I'm going to include the equations that I've used. I'll show my work, probably right here, maybe right here, wherever I have more space. But anyways, so you'll be able to follow along if you want to check my math. Please check my math. So let's start with ethyl hexanoate. And what do we know about ethyl hexanoate? We know that it smells like apples and can also smell like guava and strawberries, but that doesn't help us with the calculations. We know its molar mass, and based on some research, I found the odor detection threshold is pretty low. It's between 0.3 and 5 ppb, parts per billion. So for this calculation, I'm going to assume 5 parts per billion because, yeah, that's what I chose. We also know, based on the science and commerce of whiskey, that the concentration of ethyl hexanoate in an aged malt whiskey is 2 milligrams per liter of ethanol. And after doing some math that I won't bore you with, well, unless you want to follow along, this equates to a mole fraction of 1.7 times 10 to the negative 7 in a 50% ABV spirit. So this is also an assumption that I'm making, is that we're looking at a 50% ABV spirit. I was also able to calculate the vapor pressure of pure ethyl hexanoate at 20 degrees Celsius, which is also like 68 degrees Fahrenheit, which allowed me to calculate the partial pressure using the liquid mole fraction and Raoult's law, which again is assuming ideal mixture. This allowed me to figure out the corresponding concentration of the vapor in air, which I'm going to assume is the concentration just above the surface of the spirit. So now we have almost everything to calculate the time that it takes for ethyl hexanoate to reach its detection threshold at the top of the Glencairn. But first we need to calculate the diffusion rate of ethyl hexanoate through air, meaning how fast are those molecules moving. through air, stagnant air. And I did that. Actually, I let ChatGPT do that calculation for me, and it used Fuller, Shetler, and Giddings correlation. At the temperature of 20 degrees Celsius or 68 degrees Fahrenheit, that was estimated to be 0.053 centimeters squared per second. So now we can calculate the diffusion time using Fick's second law of diffusion, which involves second derivatives. And boy, has it been a while since I did those. So I assumed the initial concentration of the vapor was 0, that the surface concentration was what I just mentioned, right? The partial pressure right above the surface, and that the distance to the top of the Glencairn from the surface of the spirit was 6.5 centimeters. Based on all of this and looking at an error function table, I solved for time. And that calculation told me that it should take about 6.8 minutes for the concentration of ethyl hexanoate to reach our minimum detection threshold at the top of a Glencairn. Cool. Of course, this is going to be less time if you're more sensitive to ethyl hexanoate and can detect it at lower concentrations. Plus, the act of pouring the spirit into your glass as well as air moving above the glass will probably speed things up. So I think that's a pretty conservative estimate, but I'm happy with it. Now let's compare this to ethanol. How quickly does ethanol reach minimum detection threshold at the top of the Glencairn? So I did the same calculations for ethanol as I did for ethyl hexanoate. I found the molar fraction in the liquid for a 50% ABV spirit, which allowed me to calculate the partial pressure and then the molar fraction of the vapor at the surface. I also calculated ChatGPT calculated the diffusion rate using the same method, and I found that the odor detection threshold for ethanol, the minimum odor detection threshold is 80 parts per million, 80 ppm, which is much higher than ethyl hexanoate, which is probably a good thing because there's so much more ethanol than ethyl hexanoate. All that was plugged into Fick's second law of diffusion. I looked at the error function table again, and finally I solved for time. And as you may have guessed, ethanol reaches odor detection thresholds in way less time than ethyl hexanoate. It only takes about 34 seconds. So there's mathematical proof right there that ethanol is probably going to be the first thing that you smell when you pour a glass of booze. And then after a little bit of time, you should be able to pick out other aroma compounds like ethyl hexanoate. But as I said, you're pouring the spirit into your glass, and ethanol and water mixtures deviate from ideal behavior. So this calculation was a gross oversimplification of what's actually happening in your glass. Like diffusion into the headspace is happening as you're pouring the spirit into the glass and as the spirit's getting agitated. But it was cool to show this calculation, and it shows that letting your spirit sit in the glass for like 5 to 10 minutes seems like a scientifically sound idea. That's a lot of talking for me, so let's wrap this video up. I do want to say a huge shout out, a huge thank you to my Patreons for helping to support me, helping to support the channel. They got to see this calculation a few days ago when I did it. They got the kind of Cliff Notes version of it. And yeah, one of my Patreons was the person who suggested that I do this video. So if you, the viewer, would also like to support the channel, the YouTube things, like, subscribe, comment, share with friends, would be great. And if you want to join us over on Patreon, I'd be even more thankful. And if you want to, I've got a link in the description below where you can join us over there. But yeah, in summary, in order for us to smell various aroma compounds in spirits, right, we need those aroma compounds to make their way to the surface of the spirit and then volatilize into the headspace, into the glass at high enough concentrations so that we are able to detect them. And it's clear that aroma compounds, as well as ethanol, prefer to orient themselves at the very, very surface of the liquid, which means that they're able to make their way into the gas phase. into the headspace. As we showed, ethanol is probably most likely to diffuse to high enough concentrations for us to smell it pretty quickly. While it might take some of the other compounds, right, especially the longer chain compounds, a little bit longer to travel up through the headspace of the glass. So maybe next time that you pour yourself a glass, give it 5 to 10 minutes and see how it evolves. I just got back from Havasupai Falls from camping, and I feel like I should have eased myself back into doing YouTube videos with doing a tasting or something, but I have decided to do something extremely nerdy. Yeah, we're going extremely nerdy with this one. So